Okay, so for warm-up, recap. Y equals 1 over x. When you plug in all of these values, you get their outputs. We talked about how 0, if you plug in 0, you get an undefined situation. You get an undefined situation, so you can't use 0 as an input. That's going to be huge when we talk about domain today. Domain talks about what you can plug in. So when we talk about the domain, we cannot plug in 0. All right. 9.2, we're going to graph simple rational functions. I want you to recognize that simple does not mean easy. Simple does not mean easy. Simple means this is going to be the easiest of the group from chapter 9, FYI. So simple does not mean easy. It's just the easiest out of what we're about to do later on. This is going to take us 2 days at least. All right. So first off, definitions. You already have this on your paper, but let's recap, or let's actually, I guess not recap. You've never been capped. A rational function is a function of the form f of x equal to p of x over q of x. This is this entire chapter where you have a polynomial over another polynomial. And what does this look like in a graph? Now, warm up, what was the polynomial in the top? In warm up, what was the polynomial in the top? Anybody? It was a 1. We call that a constant function because k was a constant number. So 1, it's a constant. Q of x, what was the polynomial in the denominator? X, otherwise known as a linear function. This is why we are going from chapter 6, all about polynomials, to chapter 9, all about rational functions, where it combines polynomials by dividing them. What? And then there's like synthetic division. What? Okay. Also, we have to stress p of x and q of x are polynomials, but q of x cannot be a constant function of 0. Q of x cannot be a constant function of 0 because we already talked about how that would be undefined. All right. Basic rational function. Here's what we're going to do. We're going to use what we had for warm-up and fill out this T-chart and see what the graph looks like. So using some of the inputs and more, because we didn't technically plug in negative 2/3, let's put in their outputs. And notice, wait, my T-chart also has a y, which we interpret as the outputs. So let's make some notices. We talked about in warm-up how if you take 1 over anything, it kind of becomes reciprocal, like negative 2/3, 1 over negative 2/3 becomes its reciprocal, negative 3/2. Notice how, okay, we can kind of see a trend. As we go left, as we start going left, we start flattening out. As we go to the right, we start flattening out. But what about around 0? What if we actually, so I'm going to add in some values. What would happen if you plugged in 1/10? What would be that output? So 1 over 1/10, it'd be the reciprocal of 10. Can I plot that point? And then what about negative 1/10? Well, that would be negative 10. So these figures, I'm going to show you, start having a particular shape, because we talked about in warm-up how 0 cannot be an input. So notice this point is very close to having an input of 0. Both of these inputs are close to having an input of 0. But you can never actually have an input of 0. So this is what happens. We start getting this shape called a hyperbola. And these hyperbolas have some restrictions. One of the restrictions is part of the domain, which we will be asked in homework tomorrow. Part of the domain, x can't be 0. The input can't be 0. But also notice about the output. There's actually a value that never happens. One of the outputs never happen. This is telling me whenever we start sloping off, that means an output won't ever be a number. We're never actually going to equal 0. There are these things called asymptotes. Asymptotes. And it's created by these things. If you have color, get out some color. These domain and range restrictions create asymptotes. And I'm going to highlight in the picture where these asymptotes are located. In this simple graph, one of the asymptotes is on the y-axis. And one of the asymptotes is on the x-axis. These visually show the restrictions in your domain and range. What can x never be? What can y never be? So in the next slide, graph tendencies of these new rational functions. Anytime you take a polynomial, divide it by a polynomial. These are the things that pop up. First off, the shape is called a hyperbola. There's now going to be a horizontal asymptote. That's a restriction on your range. So you might want to put down by it a range restriction. Anytime we're talking about range, that's the horizontal asymptote. If you can't remember horizontal, look in my room behind my desk. I've got a horizontal picture up here that kind of helps you remember what horizon looks like, or what horizontal looks like. Looks like a horizon. So, horizontal asymptote affects the range. Vertical asymptote, so one that runs up and down, it affects your domain. What can you not put in your calculator? So, if you don't remember what range and domain are, then put the coordinates by it. So if you don't know that domain deals with your x's, put down that it deals with your x's. All right. And then there's two symmetrical parts called branches. These, when you combine a couple branches, that creates the hyperbola. Now, hold on. My bad. Only in simple graphs, simple rational functions, does a hyperbola exist. We're also going to see some rational functions graph that it is not a hyperbola. A hyperbola only has two symmetrical parts called the branches. But we're going to see some crazy ones. All right, well, let's try to graph this, shall we? And we're going to state the domain and range.